Hi, my name is Junxiao. I am a guest researcher at the National Institute of Standards and Technology. Today I'm presenting our paper NDN-DPDK, NDN forwarding at 100 gigabits per second on commodity hardware. During the past 10 years of NDN research, we identified that NDN needs a high-speed forwarder. The use case for a high-speed forwarder includes data-intensive science, live video streaming, and many other applications. So we started the NDN-DPDK project. The performance goal is to achieve line speed on commodity hardware. In order to get there, we are pursuing two avenues. First, we want to adopt better algorithms and data structures, or the so-called network algorithmics. Second, we want to reduce overhead in the library and kernel. For this, we are using Data Plane Development Kit, or the DPDK. DPDK is a set of libraries to accelerate packet processing workloads. Its main feature includes a multi-threading library allows us to use all available CPU cores for packet processing. The ring buffer queue library allows us to efficiently transfer packets between threads. Huge page-backed memory pools means there is no memory allocation in the fast data path. And most importantly, DPDK provides some user space Ethernet adapter drivers so that packets can be sent and received without going through the kernel. NDN-DPDK is a complete implementation of the NDN data plane. Compared to parallel work, most other papers, they focus on a subset of the data plane functionality. NDN-DPDK is running on real hardware, while some of the previous papers, they rely on simulations as their evaluation. Most importantly, NDN-DPDK can support a full NDN protocol and name matching semantics. In particular, one of the NDN protocol design principles is name discovery. It allows the interest to use a partial name to find the data, which means interest name can be a prefix of the data name. While a lot of previous designs, they lack support for this prefix match and instead requires interest and data to have the same name for exact match only. NDN-DPDK adopts a multi-threaded architecture shown in this diagram. The threads are divided into three stages: input stage, forwarding stage, and output stage. In the input stage, the input thread receives Ethernet frames from Ethernet adapters, decode those packets, perform NDN-LP reassembly if the packet were fragmented. Then they will dispatch packet to the forwarding thread using their name or other criteria which I will describe later. The forwarding threads, they each contain the PIT, CS, FIB, and forwarding strategies, and they will process the packet according to the NDN protocol. And finally, the packet will be transmitted with the output threads. NDN-DPDK's data structure design took a few inspirations from the ANCS 13 paper named Data Networking on a Router, Fast and DOS-Resistant Forwarding with Hash Tables. In particular, we adopted the two-stage longest prefix match algorithm. On the engineering side, we use read-copy update or RCU mechanism to protect the FIB entry so that it can be updated from management and routing protocols. We also merged the strategy choice onto the FIB entrance. Instead of using a separate strategy choice table, this allows the forwarding thread to perform only one namespace-based lookup and determine both the strategy and the next ops. The measurement information as well as the packet counters used in the forwarding strategy is also stored in a dynamic portion of the FIB entry. That portion can be updated without going through the RCU mechanism. We replicate the FIB onto every NUMA socket. Here, NUMA stands for non-uniform memory access. In modern server hardware, if the server has multiple CPU, each CPU along with some amount of memory and PCI devices are organized as NUMA socket. A CPU can efficiently access the memory in the same NUMA socket, but it will incur higher latency if it tries to access memory in another NUMA socket, or the so-called non-local memory access. By having a copy of fib in each NUMA socket, the forwarding thread can avoid the non-local memory access during fib lookups, and therefore run faster. As shown in the architecture diagram, each forwarding thread has a private instance of the pending interest table data structure. They are implemented with non-thread safe hash tables, and update to the PIT does not need RCU mechanism. But this means only one forwarding thread has information about each pending interest in its PIT. This imposes three requirements on packet dispatching from the input thread. First, if two interests share the same name, they must be dispatched to the same forwarding thread. This is required by interest aggregation and loop prevention. Second, if two interests share a common name prefix, they should be dispatched to the same forwarding thread. This makes forwarding thread effective by being able to collect per prefix measurements. The third requirement is for a data or NAC packet, they must be dispatched to the same forwarding thread that processes the interest, because only the PIT in that forwarding thread has information about the pending interest, and they can allow the data or NAC to go back to the downstream. So how do we do the dispatching? For interest packet, we dispatch them by their name prefix. Speaking of name prefix, you will think about the fib, because fib is a mapping from name prefix to a list of next hops and other information. However, fib is a fairly complicated data structure. It is too expensive to perform fib lookups in the input thread. We need a much simpler data structure. So we designed the name dispatch table, NDT. NDT is a mapping from hash of name prefix to forwarding thread ID. It is implemented with a linear array of atomic integers, so it is much simpler than the hash table-based fib. So how it works? When input thread receives interest, it will compute the hash of the first two name component, but according to your name network environment, you can change the number too. It is configurable. Then it will choose the NDT entry using the last few bits of the hash value. Then the value of that NDT entry indicates which forwarding thread should process the packet. In this case, it's forwarding thread 1, so the interest is dispatched to forwarding thread 1. This mechanism allows interest with the same name or sharing a common name prefix to go to the same forwarding thread, and thus fulfilling the first and the second requirement I mentioned earlier. For data packets, the name dispatching based on NDT would work most of the time except one case. Suppose the interest name is /a, it goes to the forwarding thread identified by the hash of /a. But NDN allows interest and data to have prefix match, so data name could be longer than that. The data name here is /a/b/1. It would go to the NDT entry identify the hash of /a/b, which might be a different forwarding thread, and that does not know about the pending interest. To solve this problem, we introduce PIT token. We use PIT token to associate interest and data. PIT token is an opaque token carried in a hop-by-hop field. It is part of the NDN link protocol. Every outgoing interest from NDN-DPDK forward carries a PIT token, and the upstream node is expected to put the same PIT token in data or NAC packet in reply to an interest. NDN-DPDK's PIT token contains two parts, a forwarding thread ID and a PIT entry index. Here is how it works. First, the downstream node sends us an interest. It might carry a PIT token, but we don't interpret the structure of that PIT token since it is an opaque field. In our input thread, it uses the name prefix to look up the name dispatch table, and in this case, it determines that forwarding thread 1 should be handling this interest. The forwarding thread will insert the PIT entry, and in the PIT entry, it will remember the downstream's PIT token. Then in the outgoing interest, it carries our own PIT token, which indicates the forwarding thread ID is 1, and it also has a pit entry index. The upstream node can forward or answer that interest, and in the data packet coming back, it is required to carry the same pit token. In our input thread, it will look at the forwarding thread ID portion of the pit token to dispatch to the corresponding forwarding thread. In this case, it is forwarding thread 1. And the forwarding thread can use the pit entry index portion of the pit token to accelerate pit lookup. But after finding the pit entry, it is still required to check that the data packet actually satisfied the interest using name matching. This is to protect against a malicious party sending out outdated or incorrect pit tokens. And finally, the outgoing data packet carries the downstream pit token we remembered earlier in the pit entry, so that the downstream node can match up its interest and data as well. One of NDN protocol design principle is in-network name discovery, in which interest should be able to use incomplete names to retrieve data packet. But our content store is a hash table. Hash table only supports exact match. In order to have prefix match in the content store, we introduce indirect entrance. Suppose interest AB was satisfied by data packet ABC1. We first insert a direct entry ABC1. It contains the data packet itself, and this entry can be used to satisfy future interest with an exact name ABC1. We also insert another entry, the indirect entry, named after the interest AB. This can satisfy future interest with the same prefix name AB. The indirect entry does not contain the data packet. It has a pointer or reference to the direct entry. But for indirect entries to work, the consumers are expected to use a consistent name for name discovery. If the consumer is using a different name to do name discovery, for example, ABC, the new interest cannot be satisfied by the content store since it cannot find the entry, so that it has to be forwarded to the upstream and probably satisfied by the producer. But after that, it will get another indirect entry pointing to the same direct entry without duplicating data packet storage. Following the idea in the ANCS 13 paper I referenced earlier, we combined the PIT and the CS into a single hash table called the PIT-CS composite table, but then we expanded from that design in several places. First, in our name-based hash table index, we include not only the interest or data name, but also the chosen forwarding hint delegation. This allows our forwarder to securely support forwarding hints. Then we added a token hash table. It is keyed by a 48-bit token, which is the PIT entry index portion of the PIT token as appeared in the packet. This allows us to efficiently locate the PIT entry when the data packet comes back. Within a PCC entry, we can have one or more PIT entries. It has a copy of the interest, records about the downstream and upstream phases. In order to support forwarding strategies, there is also a strategy scratch area for forwarding strategy to store measurements and decision-related information regarding a PIT entry. This differs from the fib entry-based strategy scratch area, which is suitable for namespace-related information. The PCC entry can also have either a direct or indirect CS entry. Both of them contain some linked list nodes in order to support ARC or LRU cache replacement policies. Next up, I will present our benchmarks. We did our benchmarks in a simple 3-node topology. There are 2 traffic generators fetching data from each other through a forwarder. The consumers has cubic-like congestion control algorithm. The physical machine has 2 Intel Cascade Lake CPUs and a number of Mellanox Connect X5 100 gigabits per second Ethernet adapters. The big news is we made it to 100 gigabits per second. We measured the aggregate data forwarding rate from the consumers. This metric only counts received data packet and does not count retransmissions. Then we multiply that by the payload size. And with 8 forwarding threads, we can get up to 108 gigabits per second. The same experiment also shows us that payload size has low impact on data forwarding rate. Then we start changing the number of forwarding threads. The expectation is if we have more forwarding threads, we should get a higher data forwarding rate. But in reality, when we increase from 1 to 2 and 4 forwarding threads, we are seeing linear growth in data forwarding rate. But when we have more than 8 forwarding threads, there is no more improvement. The data forwarding rate plateaus at 8 forwarding threads. Our analysis indicates that the input thread might be the bottleneck because the current forward architecture only allows one input thread per phase. In our future work, I'm going to describe how we plan to address this bottleneck. As I introduced earlier, on a multi-CPU machine, each CPU, some memory, and PCI devices such as Ethernet adapters belong to a NUMA socket. We can either connect both traffic generators to the same NUMA socket, or we can move one of them to the other NUMA socket, forcing all the traffic to cross NUMA boundary and incur higher latency due to non-local memory access. In our experiment, we found that if traffic has to cross NUMA boundary, the throughput is up to 20% slower. We measure the forwarding performance with a large fib up to 1 million entrants. As we can see from the numbers, aggregate data forwarding rate remains stable as the fib grows. Ingress latency is increased marginally. We tested the forwarding performance with a large content store. In order to generate CS hits, we need to use a different benchmark topology. There are 2 consumers connected on different Ethernet adapters and fetching the same data through the forwarder from a producer. In the plot, we are showing the content store hit ratio and the data forwarding rate. Each of the 4 colored dots represent a different scenario. Each scenario has a content store capacity and whether we are using exact or prefix match. The content store capacity is up to 1 million data packets in each of the 8 forwarding threads. For the prefix match scenario, the producer will append an extra suffix name component when it replies an interest with data. As we can see, prefix match has lower data forwarding rate than exact match because the content store need to maintain both the direct and indirect entrance. We can also see that a higher CS hit ratio results in a higher data forwarding rate because the forwarder only need to process fewer packets. We also tested the packet processing latency with large content store capacity. As we can see from the CDF plots, exact match and prefix match, as well as different capacity, results in similar latencies. In the worst case of those scenarios, at 90th percentile, the interest processing latency is just under 5 milliseconds, while the data processing latency is about half a millisecond. In our future work, the most important is removing the input thread bottleneck. This includes some design changes to allow having multiple input threads per phase. Then we want to explore using the receive side scaling feature of the existing Ethernet adapters to dispatch data or NAC packets. Then we can consider using extended Berkeley packet filter or FPGA hardware logic to dispatch the interest packet using the name dispatch table. We also want to expand the content store to NVMe disk storage. We want to perform load balancing among forwarding threads by changing NDT entrance automatically. And since 200 gigabits per second hardware is out, we want to do further performance profiling and improvement to reach that line speed. NDN-DPDK codebase is open source, published on GitHub. It contains the forwarder, the traffic generators, some GraphQL-based management tools, and the NDN-Go library for application development. The licensing is dedicated to public domain. Thank you for your attention.